So we are going to continue our discussion on the isomorphous systems. In the last class I told you the basic features of the binary isomorphous systems, and today we are going to continue on the same thing. Just to give a recap of the whole thing, if we add one element to other, we form a binary alloy. So in a system like two components, we have three variables to be considered. The first is the temperature, second one is the pressure, and third one is the composition of one of the components, because composition of the other component can be easily obtained. So therefore, the isomorphous or binary phase diagrams will have three different axes: pressure, temperature, and composition. And as you know, it is not easy to deal with the three-dimensional space diagrams in the phase diagrams like binary systems. So therefore, you always take a section, and the section is always taken at 1 atmospheric pressure. Once you do that, that's what I discussed in the last class. Let me just tell you again. So in a three-dimensional section, it will look like this. We have composition axis on the x, pressure axis on the y, and temperature axis, pressure axis on the z, and temperature axis on the y. And it tells you the whole phase diagram in terms of liquid plus solid, liquid plus vapor, and vapor plus solid equilibrium. So therefore, it is very difficult to work on such a three-dimensional diagram, and to make it simpler, we take a section at 1 atmospheric pressure, and that is done here. So if I take a section at a pressure 1 atmosphere, pressure of 1 atmosphere, then it becomes P equal to 1 atmosphere. Then it becomes a two-dimensional section, because we have taken a section at 1 atmospheric pressure, so it is become a two-dimensional section. And in the two-dimensional sections, your x-axis remains as a temperature compositional axis of component B, that is xB. xB is the mole fraction of B, and y-axis is basically now temperature axis. The z-axis is completely gone. And in a simplest possible phase diagram, what is known as isomorphous phase diagrams, we have three zones. One is liquid, which is demarcated by L, other one is alpha, demarcated by solid, and in between these two we have a length separate region known as liquid plus solid, or alpha plus liquid. Okay, solid is alpha phase here. So that is how actually the phase diagram develops. Now I have given you many derivation of these different what's called the different type of solid solutions, or like substitutional solid solution or necessary solid solutions. And then finally I have shown you this slide where I talked about how to use these phase diagrams. So let us take a very simple way the Copernican phase diagram. I want to discuss you because Copernican is a important industrially important systems, and this is the first phase diagram where two metals form a isomorphous type of system. As you can see here, L stands for liquid, alpha stands for solid, and in between you have a length separate region known as alpha plus L, or L plus alpha, whatever it is. The top curve is known as liquidus, bottom of one is known as solidus. So there are two phases, liquid and solid, which are simple solid solutions, okay, and there are three phase fields here. One is liquid, other one is alpha, other one is third one is liquid plus alpha. Now here in this class, what I am going to discuss with you is that how to discuss the solidification of alloys in these systems. So obviously, to know that, we should know how to apply lever rule, and this again I have discussed in the last class. Lever rule is very simple. Suppose I have to calculate the amount of phases liquid and alpha in the two phase field inside the length separate region. What I do is that I draw a horizontal line parallel to the x-axis or compositional axis at a particular temperature Tb, and this line is drawn here like a black one, connecting the liquid and the solid phases, or liquidus and the solidus. So therefore this is a tie line you can consider, because it ties the liquidus and solidus, and in this line the one end of the line actually connects the liquid to the other end as a solid alpha. So if I consider this as a lever with fulcrum at the composition at which we want to do the calculations. So the solid phase is given by this arm, that is alpha is given by this arm divided by total arm of the lever, and total lever, and liquid is given by this arm divided by total length of the lever. That is how actually we calculate the amount of phases, and same thing is done in this slide. If I consider the composition of the alloy to be at 38% of nickel, and you draw this tie line at a temperature Tb, which is between 1200 and 1300 degrees Celsius, then you can see here that Cl is equal to basically the composition of liquid is equal to 32.8%, and C alpha is basically 43% here. You can see here, this is what the 2 points it cuts. So if you use the lever rule, you can calculate the volume fraction of the phases very easily. That is given here. Okay, volume fraction of the solid is given by R divided by R plus S. See, R divided by R plus S is 27%, 8%, and volume fraction of the liquid is given by S by R plus S. It is equal to 73%. So these are the basic things you need to know when you want to discuss the solidification of the alloys. So let me just go ahead. Now that I have given you a perspective of that, suppose if I want to study the solidification of the alloy composition, which is given by 35% of nickel. Obviously I start from the pure liquid. Pure liquid means when everything is liquid. As I know, above the liquidus, the whole alloy will be in the liquid state, and below the solidus, whole alloy will be in the solid state. Now let us follow from the high temperature to low temperature what actually happens along this vertical line, which I have drawn at 35.8% of nickel. So at point A, it is fully liquid, okay, and I am going to follow the solidification in equilibrium manner. What is the meaning of equilibrium manner? It means we give sufficient time to the system so that it remains in equilibrium state or equilibrium conditions. There is no such change which can happen as time dependent. Equilibrium means it is one state which is the final state at any time or any temperature. Okay, so basically system is kept a long time so that the compositional temperature everything gets homogenized. So at the point A, which corresponds to 1300 degrees Celsius temperature, as you have seen here 1300 degrees Celsius temperature, it is a completely liquid state because it is above the liquidus. So above liquidus everything should be liquid. Now as we cool down from A to B, P is just slightly below the liquidus temperature, just slightly below liquidus temperature. As you see, this is what the point B is. Nucleation of the solid alpha is going to happen. Obviously nucleation should have happened at a point exactly on the solidus, or on the liquidus, that is exactly on this curve, but it will not happen because of the nucleation kinetics. Because as you form a solid out of liquid, you are creating a new interface between the solid and liquid, and energy corresponding to that must be provided by the system. So that energy can only be provided if the system has finite positive energy. So as you know, at the melting temperature or the liquidus temperature, the Gibbs energy difference between the solid and liquid phase is 0. So therefore there is no available energy to the system which can be spent to create the interface between solid and liquid, and that is why you need to cool down below the liquidus to form solid alpha. So that is what I have drawn here. So I put a point B here, and that point actually corresponding to the temperature little below the liquidus at which the solid alpha can nucleate, and we have given the solid alpha will have composition of 46% of nickel and remaining liquid will have composition of 35% nickel. It will remain as a 35% nickel because there is very little amount of solid alpha has formed. Nuclei which will be formed in the liquid will be a very small size, so therefore their volume fraction or amount of the phase is very small. So liquid will be almost at the same composition at which you started. Now from point B to C, as we cool it down, what is going to happen? You can clearly see, if I go down from B to C, solid will form as a composition which is given by this point 43% of nickel, and liquid will have composition 32% nickel. These two curves on which the tie lines are actually falling on will give you these compositions of the solid and liquid as I told you earlier. So that means the initial solid which is formed, which is a composition of 46% nickel, but at point C, which is at a lower temperature than point B, the solid which will form will a composition 43%. So there is a compositional difference between these two solids which is formed. So from point B to point C, the microstructurally or feature wise, these nuclei which is formed in the liquid will grow, will become bigger, but as they grow the composition is changing as per the phase diagram. So therefore that must be adjusted, properly, in the sense that we are doing this experiment in equilibrium condition. So that is why the composition will be adjusted between this solid alpha which is forming in the liquid, so that the whole solid will have homogeneous composition. There will be no compositional variation in the solid when you cool it down from B to C. This is a very important point you must remember, you should not forget, because of the change in temperature, composition of solid forming at a temperature given by point C has lower solute content or lower nickel content than at point B, but this must be adjusted at under equilibrium conditions by compositional change. So that is possible because liquid has a large pool of nickel, a liquid can provide the nickel to the solid. Now this will keep on happening as you cool it down point C to point D. D is the point which is just sitting above the solid S, and as you see here, if you come down from C to D, the composition of the nickel has decreased from 43 to 36%, okay, because the point D is lying at a much lower temperature, okay. Similarly, composition of this liquid will be given by this point which is at 24%. So therefore if I solidify an alloy from point B to point D, the solid composition will keep on changing at any temperature, that is given by this solid S curve. So this must be adjusted in such a way that composition of solid which is forming at any temperature will be of uniform composition. And as you understand, this is only possible, the diffusion of the solid which is forming at any temperature with the solid which is previously formed is possible only when we can keep at the temperature for a long time. Why? Because we have to give time for diffusion to happen. It is like this, at point B I form a solid whose composition is 46%. Now at point C I form a solid whose composition is 43% nickel. So now because these two solids has different compositions, in fact solid inside has a higher nickel than the solid outside, you need diffusion to happen from inside to outside, otherwise the whole thing will not be of uniform composition. This is only possible only when you keep this whole system at point C for a long time to equilibrate, and similarly from point C to point D. Okay, so at point E the whole thing will be completely solid because point E is sitting much lower than the solid S curve. So at point E you will have a complete solid forming, and this solid will have uniform composition of 35% of nickel in all grains of the solid, and solidification will be completed. So I hope by this discussion you have understood how we can solidify an alloy from liquid state to solid state under equilibrium conditions. But you know, you cannot have equilibrium conditions under real situations. Why? Because in real situation you cannot keep the sample at a particular temperature for infinitely long time, that is not possible. In industrial scale time is the money, so therefore you cannot keep the sample at a temperature suppose at point C or point D for sufficiently long time for it to equilibrate, and thus things will change. So that is why I am going to discuss you the next, what will happen if we solidify the alloy under non-equilibrium conditions. What is that? If I solidify an alloy in such a way that I do not keep sufficient time at different points like B, C, D, so what will happen? That is very simple. This is shown here. As I said, the first solid which is formed inside core will have a composition of 46% nickel. But the last solid which will form will have a composition of less than 35% of nickel. So in between also there are many layers of solid will form. As you see in the slide here, as you come from B to C, C to D, what is happening? B will have 46% nickel, C will have 43% nickel, D will have 36% nickel. So you are creating a gradient from the core to the periphery of the solid in which nickel concentration is varying from 46 to 36% or even less. So that is why actually the solid which will form under non-equilibrium conditions will have this compositional gradient in the solid, and this compositional gradient will create further problem. What is the problem it will create? Because there is a compositional gradient, the solid will be of non-uniform composition from center to the periphery, and because of non-uniform composition properties will be non-uniform, and this is not good. And this kind of situation in the literature is known as core. What is this? Is known as scoring actually, C-O-R-I-N-G. Why it is known as scoring? Because we form compositional variation from the core to the periphery, that is why it is known as scoring. And this is a very typical feature in any industrial practiced alloys. You can't avoid it, it is very difficult. So all the solidified products in industry, because of time constraint or practical limitations, will have core microstructures, and these core microstructures must be removed before you apply these alloys for certain applications. So by this lecture you are able to understand how the core microstructure will form. This is mainly because of the non-equilibrium nature of the solidification process, in which the system is forming solid whose composition varies from the center or core to the periphery, and this variation is going to create compositional modulations or variations, and this can only be removed by further heat treatments, that is known as annealing. So if I take this solid piece, heat it up to high temperatures, obviously below the solidus temperature, for sufficiently long time, the diffusion of the atoms will happen from center to the periphery, and this can be annealed out. So this is what is shown here. If I have a fast rate of cooling, which is normally the practiced thing in the industry, we will have a core microstructure compared to the slow rate of cooling in which the uniform composition possible, and this is equivalent to equilibrium structure. But it is not possible to follow the slow rate of cooling in the actual practical applications, so that is why you will have lot of these coring happening in the microstructures. Let me just show you a few pictures. Let us take this one. This is basically a picture taken in our laboratories and taken from the book of Professor S.P. Gupta. Okay, he himself has gathered for copper nickel alloy. As you can see here, this is a typical dendritic microstructures. We will discuss why dendrites form later, but this is a typical dendritic microstructure. But if I clearly look at one dendrite, suppose if I look at this dendrite, you can see center is very light, but the peripheries are dark. Normally we prepare samples in metallographically by using certain polishing and then followed by etching. If you etch it, the basically etching means using of certain kind of chemical agents to remove certain things in the microstructure. Like in copper nickel alloy you use ferric chloride as agent. So what it will do, ferric chloride will react with copper and remove the regions where copper is present, and if I remove those regions, the regions will form microdents, and therefore in optical microscopically they will look as dark. So here you can see here the dendritic core here are rich in nickel, that is what we have seen in the earlier picture. On the other hand, dendritic peripheries are rich in copper or otherwise lean in nickel. So therefore initially whatever solid is formed at the center of the dendrites, they are nickel rich, but periphery has copper rich or nickel lean, and that is the mainly that known as coring, and that is what exactly I discussed. So in all these dendrites you see here, anywhere you take, you can clearly see the core microstructures, and this is bad news for the applications. Why? Because you have non-uniformity compositions, non-uniformity composition to non-uniformity properties and cannot be applied. So therefore this particular sample needs to be annealed or heat treated. Now before I conclude this lecture, let me just, this is one such picture of copper nickel alloy. You can see that this is the schematic picture of the dendrites, which is core. Central will have lot of nickel, periphery you have lot of copper, and you can see here the way it is done is like this. This is the central dendrite, okay. Then peripheral ones are like this done. I am drawing it again for your help. And finally, so therefore these are the layers. Every temperature you draw, you form layers. So central to periphery, the copper concentration is increasing and nickel concentration is decreasing. So copper concentration increases, okay, and nickel concentration decreases from central to periphery. So nickel will decrease. That is what is happening because of coring. This is the low magnification optical micrograph, where you can see that these are the copper rich regions, okay, and which is, these are looks like dark, and these white regions are copper lean regions, which are nickel rich regions, in other words. Now many people actually modify this phase diagram, which I will do here. We can actually modify these phase diagrams, okay. So how we can modify this phase diagram? Suppose this is my alloy composition C0, okay, and I know that solidification will take place in this manner, non-nuclear manner. So we can actually see that the phase diagram will have will be looking like this. Why? That's because a very simple thing we have to understand. If if it's not clear, I will discuss in the next class again. This is very simple, that this solid which is forming, suppose this first solid which is formed at point B, which is a composition of suppose C0, then second solid has a composition of C1, and C1 is richer than C0. So the average composition of the solid will lie between C1 and C0. So that is why if you draw this tie line, which will not fall on the solid S, it will fall between these 2 points. So therefore this point will lie this. This is for point B, okay. Let me just go back there here, okay. So the average composition of the solid between B and C will be falling between B and C, 46 and 43, and that must be lying somewhere here between 43 46, which is basically 44, something like that. 43 plus 46 is how much? Is 9, 8, so 44.5. So 44.5, but temperature is same as this tie line. So that is why this point will be somewhere there, and if you do this for every tie line like that, okay, so you will get a curve like this, and this is what I have drawn. So this is known as non-equilibrium curve. So because of this non-equilibrium curve extension, solidification will be over at point suppose F, which is lower than point D, or lower than the liquidus temperature. So under non-equilibrium condition, solidification will never finish at the solidus temperature, it will get over at a temperature given by point F, okay. I hope I am clear a little bit. So let me just again draw this thing and show you. Let me just again draw it and show you, or later again tell you how it is possible, okay. Just little bit erasing part will help you. So what I am saying is that from point B to point C, I have two different solid forming 43 and 46%. So average composition of the solid at point C is given by, basically average has to be calculated using the how much is the mass of the solid which form at point B and point C. But anyway, for the sake of understanding, let us assume that thickness of the layers are similar at point B and point C. Therefore average composition will be given by average of these two, 46 and 43, and that is 44.5%, and that 44.5% line point will be falling somewhere there. Now but my alloy system is at point temperature corresponding to point C, right? This is what it is. So therefore if I have to get this point, what I will do, I extend this vertical line or horizontal line this way and drop a vertical from this 44.5 points to this. So this is my new equilibrium point or new non-equilibrium point, okay, at temperature given by point C. Similarly at point, suppose at G, this is my line, so this will be point given by this point. Similarly at point D, this will be given here. So I can join these points and get a line which will be then meeting at point F. So that is in all the books you will find this is what it will be drawn, Okay, I will just going to draw it again for you. This is my temperature, this is the composition. So this whole thing will be falling like this. This is the non-equilibrium solidus line, solidus curve. Then and the equilibrium one is this one. This is equilibrium solidus. So I hope with this I made you convinced that the solidification of this kind of isomorphous alloys is not so simple. It's rather it depends on how fast you cool or how fast you solidify. And normal situation solidification will be happening in a non-nuclear manner, and this will lead to core microstructures, and by this we can actually change the phase diagram. So in the next class I will discuss with you how actually we can what are the conditions for isomorphous phase diagrams and how we can change the phase diagrams and move into eutectic systems.